All right, so to fill in our library of functions here, we are going to be following a method that you can actually use for any type of function in the future. If you generally just want to see what something looks like and you have an equation, you can make a table of values. So that just means you're going to be picking some x values, you're going to plug it into the equation to get the corresponding y value, and what that creates is just a big list of ordered pairs. Then you're going to take those ordered pairs and put them onto the graph. And so when picking x values, I always like to pick some negatives and also some positives. So the first equation here actually should look familiar to us, y equals x, because this is something that's linear. I'm going to go ahead and give a name to this. But notice how it's in the form of y equals mx plus b. So this one actually has a y-intercept of 0 and a slope of 1. Whoops, let's unfreeze that. Where's my thing? All right, so that we can actually see what's being written down. Sorry about that. All right, so we have, up until this point, learned methods for how we can graph using a y-intercept and using a slope. So we could think about what that would look like. With the table of values, we're going to get the exact same graph. And this one is actually going to be a very simple table for us to fill in because we're just going to think about the x value of -3 being plugged in right here. So if x is -3 and if x is equal to y, then that means that y should also be -3. So that's going to actually be the first ordered pair that we can plot over here on the graph. So from the center, this is called the origin, we're going to go 3 spaces to the left. So that's when x is -3, and then we're going to go 3 spaces down, that's when y is -3. And then we're just going to keep going. So again, if x is equal to y, if x is -2, then y is -2. And let's go ahead and plot that next point, -2, -2. Then we have the ordered pair -1, -1. It's going to pass through 0, 0. 1, 1, 2, 2, and 3, 3. All right, and just as we've done in the past when we have a set of points, we'll go ahead and draw a straight line through to connect them. Now, if we look back to what we already know about slope and y-intercept, sure enough, there is a y-intercept of 0, just as we expected. And if we think about the slope, the rise over the run, we can see, yep, that's a positive slope. And going from one point to the next, it's up 1 over 1, up 1 over 1. And so sure enough, that ratio, 1 over 1, that simplifies down to 1. All right, we're going to take a look now at a new equation. So this one is now y equals x squared. So when we have the x that's being squared, this falls into a family of functions called quadratic. And we don't define quadratic functions by slope or y-intercept. We only use slope and y-intercept for linear. So there's some different things altogether if it's quadratic. For now, we are just going to look at the numbers in the table. Now, let's see what happens if we were to plug in the x value of -3. I'm just going to write this off to the side here. If something is squared, that means that it is being multiplied by itself. So that really means -3 times -3. But when you multiply a negative by a negative, it turns into a positive. So when x is -3, the y value is 9. Let's go ahead and find that point here on the graph. So x is -3, y value is 9, is going to be right there. All right, and then continuing forward, -2 squared means -2 times -2. That's going to turn into +4. When we do -1 squared, -1 times -1 is +1. Let's think about 0 squared. So we talked a lot about how 0 multiplied by anything is equal to 0. even if it's being multiplied by 0. So if 0 gets multiplied by itself, nothing changes, it's still 0. All right, and then I think it gets a little easier when we move into the positive values. So 1 squared, 1 times 1 is 1, 2 squared is 4, again, and 3 squared is 9. So what's interesting here is we actually have some symmetry in our table. We're going to find that we also have some symmetry in the graph. So when we plot the points 1, 1, 2, 4, and 3, 9, we actually have, with a quadratic function, something called an axis of symmetry. It's like this invisible line that just passes through the middle, that if you were to fold the graph over that line, the right side is going to perfectly line up with the left side. We also have a special name for this graph. Do you remember what we call this shape? From Algebra 1. It starts with a P. It's called a parabola. So the parabola is this U shape. That's what's produced when we graph a quadratic function. We can tell that a function is quadratic if it involves an x squared. So we are going to actually do more work with quadratic functions in Chapter 4. So this is just a little preview to what that situation is going to look like. All right, so that's our quadratic function, y equals x squared. All right, let's continue here. So there's really not a real fancy formal name for this next one other than this is our absolute value function. We've seen the absolute value sign before back in Chapter 1, and we know that absolute value is just describing the distance that a number is away from 0 on the number line. Absolute value is going to take negative numbers and make them positive. It's going to keep positive numbers positive. So the big thing with absolute value is the output, the end result, is always a positive number. So absolute value of -3 is 3. Even when we get to the 0 here, absolute value of 0 is just 0. 0 is 0 spaces away from itself. All right, let's take a look here at what the ordered pairs will look like. So we've got -3, 3, -2, 2, -1, 1, 0, 0. Now we're going to change direction. 1, 1, 2, 2, and 3, 3. All right, so this graph has some symmetry as well, kind of like our parabola, where one side is symmetric to the other. The difference, though, is that there's no curve at all. So they're just perfectly straight lines, and this is the one that just kind of looks like a V shape. Now, here's another thing that's cool about the absolute value graph. This is actually a piecewise function, just like what we were talking about on Tuesday. If we were to define it as a piecewise function, not using the absolute value symbol, that would look like this. So we could notice here that we have a boundary line through the x value of 0. So notice that that's separating the pieces on the two sides. And on the right-hand side, that's where we have x values greater than 0. On the left side, that's where they're less than 0. I'm just going to make one circle an open circle, the other circle closed, because they're connected. And notice that the equation on this side is y equals positive 1x. It has a slope of positive 1. Y-intercept is 0. On the other side, the slope is negative 1. It's still up 1 over 1, but it's being a negative slope instead of a positive slope. That one still has a y-intercept of 0. So that's actually another way that we could write the equation for an absolute value function. If we did it in the form of a piecewise, it would look like this. So it's equal to -x for x values less than 0. Otherwise, it's equal to positive x for x values greater than 0. All right, and again, not really a special name for the last function other than recognizing the symbol that's being used. Notice how now the x is inside of the square root symbol. So we call this one the square root function. So you might notice something right at the start, that it's not the exact same table of values that we're filling out. We don't have any negative values. And so let's think about that. The reason that we don't have any negatives here is because we can't do the square root of a negative number. So for example, like if we were to put something in there like -4, that doesn't actually work, because when we're trying to figure out what the square root is, the square root means what number multiplied by itself equals -4. Well, if you think about a number being multiplied by itself, if it was 2, positive 2, that multiplied by itself is going to be +4. While if it was -2, -2 multiplied by itself is also +4. The only way that you can multiply and get a negative is if one is positive and one is negative, but then it would be different numbers. It wouldn't be multiplied by itself. So it's not possible to square root a negative, so we're not going to have any negative values in there. In fact, the only numbers I picked were ones that we could easily take the square root of, giving us an answer that's a whole number. So let's think about this. When we do the square root of 0, what multiplied by itself equals 0? Well, that's just going to be 0. When we do the square root of 1, the number multiplied by itself that equals 1 is 1. When we do the square root of 4, the number multiplied by itself that equals 4 is 2. And then finally, when we do the square root of 9, the number multiplied by itself that equals 9 is 3. The square root function is actually like the inverse of the quadratic function that we did before. It's like taking the answers to the quadratic function and then undoing that. A way to undo something squared is to take the square root of it. So we're undoing it, getting back to the original number that we started with. Let's go ahead and see what these 4 points look like on our graph. So it is going to go through 0, 0. It's going to go through the point 1, 1. But then it's going to jump, and it's going to go over here through the point 4, 2, and then it's going to go to the point 9, 3. So it's actually kind of just this little, it starts in the center, and then it's just kind of this subtle curve that's like going upward and outward, and it just exists on that right-hand side of our graph. All right, so that's our library of functions. These are all of the original functions that we're going to be basing our transformations off of today. At the bottom of your paper, it says that these graphs are the original graphs, or here's another name that we're going to give to them. We're going to call them the parent graphs. And the goal today is we're going to see how applying changes to that original equation produces a change in the graph, and those changes are called transformations. If something transforms, it's changing. All right, so we're going to now move into exploring some different kinds of transformations. So in the next section here, we are going to begin by graphing each equation on either our graphing calculator, or you can do this on Desmos, and we're just going to draw what we see. So I'm going to model this for you using both devices. I'm going to start with the graphing calculator, and then I'll switch over to Desmos. If you're on Desmos, if you want to kind of explore and experiment and see if you can find these equations, you can do that. But I'm going to start with showing you the graphing calculator steps. So let's just talk about this first one here, y equals x squared plus 2. So on our calculator, we can enter in an equation to make a graph by pressing the y equals key. So you're going to find y equals up here in the upper left corner. And if it's all cleared out, it might look like this up here. Now, if you do see some things typed in there, you can press the button clear that's right over here. You can use the arrows to go up or down, and then just hit clear to like, backspace anything that's in there. Anytime then we want to get our variable x, we're going to press this key right here that has an x at the front. It's right next to the alpha key. When I'm demonstrating this at the front, the last key that I press is going to show up in red. So that's how we get the x. And then if we want to make it squared, we actually have a squared key. So that's right over here, like diagonal from where the 7 is. So we just turned it into x squared. And then this one was a +2. So we're just going to go ahead and add that onto the end. All right, the last thing I want you to check before you hit graph is your calculator window. And mine is a little funky from some work that I was doing yesterday. To get back to like a basic standard window, typically we do -10 to 10 in both directions, the x-axis and the y-axis, but you could like zoom out or zoom in. This is really just like telling the calculator how do you want to zoom this. And so if you do need to type it in, there's a special symbol on your calculator that's a negative sign. So it's right below the 3. It's different from the subtraction sign. So I'm going to have it go from -10 to 10 in the x direction. X scale should be set to 1. So that just means that our little increments are going to count up by 1s. And then I'm going to do the same thing here in the y direction. So -10 to +10, and then the y scale is also set to 1. Once you change the window here, you don't have to go back and change it every time. All right, when you hit graph, it's going to graph it for you. So we can see that there definitely was a change that happened from our original parabola shape. Go ahead and copy that change down onto your paper. All right, now if you are working on Desmos, we are just going to go to the URL. You're just going to type in desmos.com. And this is how it's spelled here, DESMOS. And then we're going to go ahead and click on this to launch the graphing calculator. And when you click here in the box, this is where we're going to just type our equation in. So we're going to type in y equals. Now down here in the lower left where it says show keypad, this is where we get some other options. You can type an X from your keyboard, or you can select an X from the button. And then to make it squared, there's a button that says A squared. Well, when you press that, it's going to turn it into an X squared. And look, that's our familiar parabola shape that we just saw. I'm going to go over here to get the +2, and notice how it's like the same end result of what we just saw on the calculator. All right, so on paper here, I am just going to sketch the change that I noticed when we graphed it using technology. All right, for the next one, I want to show you how you can do the absolute value sign. And so there's a little bit more work on the graphing calculator. So if that's you, let's go ahead and press y equals. And this is where we can go ahead and clear this to start to type in the next one. So in order to get to the absolute value sign, we're going to find a key that says math on it. It's just 2 spaces down from the second key. So you're going to go ahead and press math. Then we're going to arrow to the right to this menu here that represents, I think it just stands for number, M-U-M. And it's this very first option right here. So ABS, that stands for absolute value. Okay, so I'm going to press enter, and it's going to put it into the y equals here for me. Notice though that I still have to type something in. For the inside part, I'm going to type in an X. I'm going to go ahead and press the same X key that I did before. Now, I have to arrow over to the right because I need to get it outside of the absolute value, because I still want to do a -3 on the end. I just don't want to accidentally do a -3 on the inside. So now I'm going to use the subtraction key, -3, will look like that. And then we'll just go ahead and hit graph, and we can see what happens here. So yeah, that kind of looks like the parent graph, but there's definitely been a change. So we'll copy that onto our paper. On Desmos, you can clear out an equation here by pressing the X. So I'm going to start by doing y equals again. And the absolute value, that's just this button right here. So it looks like the absolute value of A. You're going to go ahead and press that. It's kind of like the graphing calculator one. Now you're going to go ahead and type in the X on the inside. We're going to have the arrow over to the right again to get on the outside of it, and then when we do the -3, we can see like the same result that we saw on the calculator. All right, so let's go back over here on paper, and I'm just gonna record, I'm gonna draw like what we saw. Okay, then the last one here, I'm gonna show you how you can do the square root symbol. So we're gonna start back over here on the graphing calculator. I'm going to go back to y equals. I'm going to press clear. Now, the square root symbol is the same button that you push when you want to square something, but you have to press the second key first. So notice how the square root symbol is the same color as your second key. So I'm going to press second, then I'm going to press that squared key, but that actually is going to give me a square root symbol. Then I'm going to go ahead and put the X in there. Same thing, you have to arrow to the right to get on the outside of it. And then this one should just have a +1 on the end. Make sure the +1 is on the outside, it's not on the inside. All right, I'm going to go ahead and hit graph. And I can see that there was a change. All right, let's go back over here to Desmos. Square root symbol is one of our options here in the keypad. It's like right next to the pi symbol. The square root of x. Arrow to the right, there's also some arrows here that you can press, like arrow to the right to get out of that. We'll go ahead and do the +1. We're seeing the same result there. Let's go ahead and draw what we saw. All right. Okay, so with that, I'm going to give you a few minutes here to answer question 2 and question 3. So I'm going to have you go ahead and use what we've seen so far to finish the questions on this page. All right, so when we added or subtracted a number on the end, hopefully you saw that it caused a vertical shift. So it either made the graph go up or it caused the graph to go down. And how do we know what direction it's going? Well, notice that the two situations that were adding a number on the end, that made our graph go up. Subtracting a number on the end caused our graph to go down. So using that, we now wanted to make some predictions of what would happen. Well, in the next one, we're subtracting 4, so I would expect it to go down 4. You could check your prediction by graphing it with technology. Adding 1 on the end, we would expect it to go up 1. Subtracting 3 on the end, we would expect it to go down 3. So generally, this first type of change that we saw is called a vertical shift because it's shifting, it's moving in a vertical direction, it's just moving up or down. All right, let's go ahead and turn our page over. We're going to take a look at part 2, and we're going to go through the same sort of set of steps here. So you're going to graph each equation on either your graphing calculator or Desmos, and then you're going to draw what you see. And what I want you to notice on this one, the format of the addition and subtraction, it is different from what we did before, because notice how here, like, we're adding inside of the function. So it's inside the parentheses. We're subtracting inside the absolute value. We're adding a number inside of the square root part. So since we took a look at how to do those with the graphing, I'm going to have you do the graph on this part. And then when you're done with that, go ahead and answer question 2. So you're going to describe what you noticed. And then you're going to make your predictions here on question 3. I'm going to go ahead, if you are using the graphing calculator like the TI-84, I'm just going to write above here the symbols of the buttons that we pushed to make each one happen. There are parentheses on the TI-84, so for like that first one, you've got parentheses above the 8 and the 9. And then I'm just going to go ahead and write in what those buttons were. So it was a little button that looks like an X squared to get the square. We had to do a few more steps on this one. We pressed the math key, then we arrowed over to the right. Underneath the number menu, we got the ABS. Just press enter. And then in order to make the square root symbol on your graphing calculator, we just press the second key, and then we press the square key. Otherwise, it should be pretty straightforward if you're doing that in Desmos. So let's take a few minutes here to work through this entire here on part 2. All right, so the big change in our equations is now we're adding or subtracting inside of the function. So like it was inside the square root symbol or it was inside the parentheses. Big changes here on our graph. So instead of it moving in the vertical direction, it's shifting in the horizontal direction. And so we saw that it's either moving to the left or it's moving to the right. However, something odd is also happening here. When we added a number inside of our function, instead of it moving in the positive direction, like instead of it moving right, which is maybe what we would expect, it's actually going the other way, which is correct. There's nothing wrong for how you typed it in and what you're looking at. When you're adding on the inside, it is going to the left. And then notice here that when we subtracted on the inside, it actually moved to the right. And so we need to be careful here with our horizontal shifting. The direction that it's going is like the opposite direction from what you would think or from what you would expect it to be. All right, so looking at our predictions here at the bottom, subtracting 3, that's going to move it to the right 3. Adding 1 on the inside is going to go left 1. Subtracting 2 on the inside is going to go right 2. And again, these types of transformations are called horizontal shifts. All right, if you're ready here, let's go ahead and turn our paper over to part 3. All right, so in this next piece, we are going to explore and see what happens if we multiply a number out in front of our equation. We have some different types of numbers here that we're going to explore with. In this first group, we have whole numbers greater than 1 in front. In the second group here, we've got some little fraction values that are less than 1. So we're going to see how those, what type of change happens. What's also going to be different here is we're going to graph these functions all together at the same time. And notice that we have the parent graph. We've got the original one listed first. So then we're going to be able to see the change of like, what's happening with the others. And so on the graphing calculator, we have many y equals that we can utilize all at the same time. On the calculator, we're going to be using y1, y2, and y3. So I'm going to show you that here in just a moment. On Desmos, if you want to get multiple equations, you just click down. So in the first position, type in what you want, click underneath that one, click underneath that one. In Desmos, it's really nice because each equation that you do, it's going to show up, it's going to have a color attached to it, and then the line that is that same color, that's the one that it is. In fact, when we're copying this down on our paper, if you have some different colors to put in your notes, feel free to take that out. Otherwise, we'll be careful to label the line with the equation so we know which one is which. Let me show you what that would look like in our graphing calculator. So looking here at the first group, I'm just going to type the x squared into the first one. Now this one will have colors as well if your screen looks like mine. If not, the graphing calculator is just going to graph the line in the order that you type it in. So it's just going to do y1 first. So watch which one that is. It'll do y2 second, and so on. All right, so I'm going to go ahead and type in the second one here with the 2 in front. And then the third one here is going to have a 3 in front. All right, so let's take a look at this one together. So I'm going to go ahead and hit graph. That did it pretty quick there. So I can see that my original graph, the x squared, that's the widest one that's showing up in blue. So I'm going to go ahead and copy that here. And if I don't have the different colors, I'm just going to go ahead and label. which equation that was. All right, the second one that I typed in was the one with the 2 in front. Notice how it's getting a little bit skinnier, it's a little bit narrower. That's going to be the red line. So the red line that I'm displaying here was the 2x squared, and then the black line is even a little bit narrower on the inside. That's the one with the 3 in front of the x squared. And you would see the same results in Desmos as well. So I'm going to go ahead and put a little bit skinnier parabola here and label that as 2x squared, and then I'm going to have an even skinnier one in the very middle. I can't quite fit, but that's the y equals 3x squared. All right, let's take a look now at the second group. So the second group now, we're just changing the parent function. But whatever happens to one type of parent function, it'll be the same effect for all of them. So we looked at parabolas here in the first one. We're going to switch over and we're going to look at absolute value when it is a fraction. So you can do this on Desmos. If you're doing it on the calculator here, that's the one I'm going to do. So with the absolute value, we just have to press that math key, go over to number to get that absolute value sign. All right, so there's the original one, and then it looks like, okay, so for your fraction, when you're typing this into your calculator or even on Desmos, you could make it a decimal if you want to just type in 0.5, or if you want it to be 1/2, what you need to do is put the 1/2 in parentheses. So do parentheses, 1 divided by 2, close the parentheses. That's how we can put a fraction into our calculator. So I'm just going to do the fraction version. All right, so we got 1/2 in front of our absolute value x, and then my next one here, I'm going to make that a 1/4. You could just do 0.25 as a decimal if that feels easier. All right, so we're going to go ahead and decompose, and okay, that's a cool looking graph. Reminds me of fireworks. It does look a little bit different. Now the original one is still in blue. Now the ones with the fractions in front are getting wider. So let's take a look at copying that onto our paper. So I'm going to start with just the original absolute value x and label that. The second one with the 1/2 in front, I saw that that got wider. It's the same V shape, it's just a wider V. And then the last one, the one with the 1/3, is even wider. All right, so now that those graphs are done, let's take a few minutes here for you to reflect and summarize what is it that you're noticing. So go ahead and answer questions 2 and 3. And I have the original one here on blue, but I'm just going to highlight. I'm going to put a highlighter around it. So we're thinking, okay, compared to the original, what happened? Okay, so hopefully we're seeing the difference here. It depends on what type of number was being multiplied in front. We had something very different happen in our two sets. So the first set there where we had a number in front greater than 1, that made our parabola shape kind of like narrower or skinnier. What actually happened, the word that we use to describe that is that it gets vertically stretched. So imagine that we have our original parabola and maybe it's like made out of silly putty. If you grab the top and bottom and stretch it out vertically, it's going to cause it to get narrower. So that's actually a vertical stretch. The other one here, when we had the absolute value, we had some fractions less than 1, and we saw just the opposite. It got wider. And so the name we give for that, eventually, we're going to call it a vertical shrink or vertically compressed. Think about, okay, instead of in the vertical direction, instead of pulling it outward like this, imagine like a big machine that's like 2 metal bars and the graph is in the middle, and the metal bars are like compressing it, like they're getting closer together, and what that's going to do is going to push that graph shape like wider and wider. So in the last part here, to make our predictions, it's just, well, if the number multiplied in front is less than 1, it'll be wider than the original. So imagine this first one here is just like a wider looking parabola shape. If the number in front is bigger than 1, and also the bigger the number is, like the narrower and skinnier it's going to be. So I just did off to the side here, that's going to be like a V shape that's like really, really narrow, because that factor of 5 is really going to stretch it out a lot. So that's the idea of multiplying a number out in the front. All right, let's go ahead and turn over to the next side. So that was part 3. We're going to turn over to the next side. This is the final piece of exploring these transformations. So in part 4, we have something similar going on here, except now so we're looking at 2 together at the same time. We're doing a lot of work with negatives. So we're going to see what happens if we have a negative out in front of our function compared to having a negative on the inside of our function. So let's take a look at each one of these. So you can do this in Desmos. I'm going to also show it just on the calculator here. The first one that we're going to look at is our quadratic function, our parabola. So when we're using our calculator and we want to get the negative sign, I mentioned this earlier, but we want to make sure that we're using the negative key. It's down here below the 3. Don't use the subtraction sign. If you use the subtraction sign, you're going to get an error. The calculator won't be able to do it. So all we're looking at here is just what happens when we put the negative in front of x squared. And this is what happened. That was interesting. All right, so we have the original x squared in blue. The negative x squared is showing up here in red. So let's go ahead and copy these. I guess even if you're using different colors, it would still be a good idea to label them. Okay, so this time, we're just looking at 2 equations together at a time. So I'm going to give you a few minutes here. I'm going to have you go ahead and finish out the rest of the graphs, and then go ahead and answer. There's 2 questions at the bottom, questions 1 and 2, where you're going to summarize and describe what you noticed. All right, so let's look at what's happening here. So for each of my pictures, I always did the original one in blue. And so we kind of have something similar happening here with the absolute value part. It looks like it just got flipped over, upside down, just like our parabola got flipped over. Even the little square root part, when we put the negative in front, it gets flipped over, upside down. Really a more formal way to say that, flipping upside down, is that we say it's a reflection, and what it's reflecting over is the x-axis. So a reflection over the x-axis means that the part here up at the top, if you fold your paper along the x-axis and it flips down, wherever it lands, that's the reflected graph. We had something different happen though for the last piece. When this one had a negative on the inside, it didn't flip over the x-axis. Instead, it looks like it flipped over sideways. But what it actually reflected over was the y-axis. So that'll happen if the negative is on the inside. So the piece over here, fold it over the y-axis, where it ends up on the other side, that'll be the reflected graph. So we will be putting in some formal words on our summary page next. But you probably were thinking something like this, like it flipped upside down. When the negative was in front, it looked like it flipped sideways when we had a negative on the inside. Now, on your summary page here, when we are filling in some examples of what each type of transformation looks like, I want you to know, keep in mind, that these transformations are going to work for any parent function. So let's just make a little note here that these work for any, meaning it could be y equals x squared, it could be the absolute value of x, or it could be the square root symbol. So to save time and to save space, I might not write an example of every single type of parent function. We might just pick one of them, but know that like if I pick the parabola shape, the x squared, it's not that like it only works for x squared, it's going to work for all of them. All right, so the first one that we talked about, we said that this was a vertical shift. Another word that we can use to say shift is a translation. And what's a little tricky about this word is that it's similar to transformation, which just means a change in general. A translation is just shifting. So it's just simply moving left or right, up or down. So that's what that is, but it's really just a vertical shift. All right, so let's put two examples in. So one example that we saw, this was in the very first part, is that if we added a number onto the end of our function, we saw that the graph moved up that many spaces. Actually, I'm not going to rephrase the word graph because it says describe how the graph changes. Well, we saw that it moved up, in this case, 2 spaces, but we could replace that 2 with like whatever the number is. So whatever the number that's being added on the end, like that's how many spaces it moved. Let's do an example of something shifting down. So maybe we have something like the absolute value of x, and then we have like a -5 on the end. So the description there is that this one moved down 5 spaces. But again, we could replace that 5 with whatever actual number we had at the end. So think of it as like a fill in the blank. It's just moving down however many spaces, matching the number in the equation. All right, we talked about horizontal shifting, also called a horizontal translation, and this is where we're going to be moving left or right. So the difference here is that we are adding or subtracting a number inside of our function. So let's use the square root function here for our first example. We're going to make one big, huge square root symbol because we need the addition or subtraction to happen on the inside. So let's start by doing an x plus 3 on the inside of our square root. And what was a little strange on this one, but we still noticed it, that when we're adding a number inside of our function, it's actually moving us to the left that many spaces. All right, next let's put in an example of subtracting on the inside of our function. I'm going to do the quadratic function on this one, so I'm going to do the x squared. When you're adding or subtracting on the inside there, you have to put in parentheses. So that's how we know that it's happening inside of the function, not on the outside. So let's go ahead and let's do like x minus 4. And what we notice here is that that would move our graph to the right. In this case, it's moving 4 spaces to the right. All right, so the last piece I'm going to add on here is just one more one more thing off to the side to help us understand the difference between the vertical shift and the horizontal shift. So vertical is always add or subtract outside of the function, whereas the horizontal shift is always adding or subtracting inside of the function. All right, so the next piece, we wanted to see the effect of multiplying a number. We looked at two different types of numbers that we could multiply out in front. So we had like whole number values that were greater than 1. It could be a fraction if it's greater than 1. It still fits into the first category. And then we looked at numbers that were like little fraction values or decimals that were less than 1. So the first situation here, and we have this example kind of already shown that if the number multiplied in front is a number that's greater than 1, it's going to be a vertical stretch. So that was like where we thought about the parabola being made of silly putty, stretching it vertically. It got skinnier, it got narrower. It could be any parent function graph, doesn't have to be a parabola, but let's just put in an example here of like doing the 3 multiplied in front of the x squared. And what we noticed about the graph is that, I'm going to say the graph got skinnier or narrower. So if this was like our original graph with a solid line, I'm going to make a new little parabola here with a dotted line just to show like that's what happens when we multiply the number in front. That's what we mean by getting skinnier or narrower. All right, the vertical shrink, or you can say vertically compressed. That's when the number multiplied out in front is something that is less than 1. Either word is fine to use there. So it works for parabolas, it works for all of the graphs, including like the absolute values. So for example, let's say we had a fraction like 1/5 out in front of the absolute value of x. And here we just noticed that the graph got wider. So on this one, like if this solid line was my original absolute value, my dotted line is showing it's like getting wider out that way. All right, and then the last ones we looked at, we saw that we had two different types of reflection. Reflection is just a fancy name for it flipping. And so the first reflection that we saw was over the x-axis, and that happens when we put a negative sign out in front of our function. I'm just going to make a little note here that the negative was in front. And what we want to say here is that this reflected, which is another name for flipped, over the x-axis. All right, and then the other scenario that we had here was looking like this. This is where we had a negative inside of our function. So instead of seeing the negative in front, I'm just going to say that the negative was inside. And for that one, we saw that it reflected or flipped sideways, but what was really happening is it was flipping over the the y-axis. All right, so here's what a problem might look like. So it's going to give us an equation, and it's going to have us first describe the transformation in words. We're also going to look for clues in the equation to figure out what the parent function is. Then we're going to use the parent function graph from the library of functions as a starting point, and then we're going to shift, move, stretch, whatever it's having us to do to make the transformed graph. All right, so let's take a look at this first equation. Now, it looks like we actually have two things going on here. The first one that I'm noticing, and I like to write like little arrows pointing to each part. I remember that when we subtracted a number on the outside, it would cause it to go down that many spaces. So it doesn't have to be super fancy. You can just say down 2. And then I'm also remembering here that when we added a number inside, so I can see that that's like inside the parenthesis part, that's going to make it go left that many spaces. I'm noticing here that it's going left 4. Now the clue that I'm looking for to find the parent function, I'm either looking for a squared symbol, I'm looking for an absolute value sign, or I'm looking for a square root symbol. But I can see clearly here that I saw a squared symbol, so the parent function is y equals x squared. Now we are going to be a little bit more particular right now with our graphs. Rather than just saying, okay, left 4, down 2, that's going to be like somewhere over here. Well, close. We're going to be more exact. And that's why we started off today looking at the ordered pairs that make each parent graph. And so remember the ordered pairs for x squared. This was from our library of functions. We have the points -3, 9, -2, 4. You can look these up in the notes packet. 1, 1, 2, 4, 3, 9. Okay, so those are the points that we're starting from. And so what I'm going to do here on my graph is I'm going to actually start with those original points. And actually when I do my parabolas normally, I start with 0, 0, and then I go out from there. So like the next step is like over 1 space, up 1 space on either side. Then we have over 2 spaces, up 4 on either side. And then it's over 3 spaces, up 9. And then I have those points there, so I know that that's my starting point. I'm not going to actually connect them here because that's not my final answer graph. Something else though that I've done in the past is sometimes I'll do a dotted line just to show like, okay, that's the original, not the final answer. I'll switch to a solid line for the transformed graph, or I'll switch colors if I have a different color. So now we're going to think about every single one of those points that we plotted is moving left 4 spaces and down 2. So we're going to actually take each point and move it. I'm going to switch to a new color. I'm going to switch here to green. I'm going to start with this bottom point here that's actually called the vertex. So that's going to go left 4, down 2. I'm going to actually show the new position of the vertex. Then I'm going to take each of these points, left 4, down 2, left 4, down 2. And then I'm going to do it over here for this set. Left 4, down 2. And the last one, left 4, down 2. I'm actually fine if we stop there. If you just want to do 5 points for your parabola, that's fine. You don't have to do the full 7. I think those 5 points give us a pretty good idea there of the shape. So the green one there, that would be our final answer. So this is what I'm looking for on your homework. I want to see the original points here, whether you have a dotted line or not, and then those exact position of points shifting over, like in this case, left 4, down 2. Okay, let's take a look at the next one here. So I want you to look at that equation, and I want you to take a moment to go ahead and write down what are the transformations, so what are the 2 things that are happening, and then I also want you to identify what is the parent function this time. All right, so hopefully on this one we should see that this is going right 3 spaces of one space. And then the clue for the parent function is that we see the square root symbol. And so going back to my library of functions from the beginning of today, I just copied over, these are the ordered pairs for that parent function. Just as we did before, I'm going to start with those. So I have 0, 0, 1, 1, 4, 2, and 9, 3. Either don't connect them or do a dotted line because that is just the original. Now, every single point is going to go to the right 3 spaces and up 1. So I'm just going to start with that first point that was at 0, 0. So right 3, up 1 is going to get me there. On the next one, if I go right 3, up 1, it actually overlaps with one of the other ones. That's okay. This one then is going to go right 3, up 1. And the last one's going to go a little off the page, so we'll just kind of estimate like right 3, up 1 would be right about there. So then with a solid line or with a different color, we'll see if I can actually draw this. There we go. All right, so that green one there is going to be our final answer. All right, we're going to do the same thing on the next one. So go and look at the next equation. I want you to describe the transformation in words. We still have 2 things happening in the next one. And then I also want you to identify the parent function. All right, so the 2 things we have happening here. So hopefully you notice this negative sign out in the very front, not on the inside. When the negative is in front, it's going to reflect it over the x-axis. Adding on the inside is going to make it go to the left. Now the clue here for the parent function is that we can see the absolute value sign. So this is our parent function. From the library, I copied over, okay, these are the ordered pairs for the absolute value of x. All right, so let's go over here and make our graph. So I'm going to start by plotting the points for the original. These points are pretty close together. I might not even do my dotted line. Okay, but that is just going to label. Okay, that was the original. When you have a reflection combined with a translation, it doesn't matter the order that you do this. So you could think about taking your original graph, you could move it left 5, and then flip it over the x-axis. Or you could flip it over the x-axis and then take that and move it left 5. It doesn't matter. It's up to you. Now with the reflection added in here, I often like to show the in-between step to make sure that my points are in the correct place. So for example, if I'm reflecting over the x-axis first, I'm going to show this in-between step, and I'm just going to switch to red. Just think about like folding my paper in half over the x-axis. Then I'm going to go ahead and shift everything left 5 spaces. So that starting point there, that vertex point, is now going to go to -5. And then I've got like my points going down for that side of the V shape. Now I've got this side. And then the green one is my final answer, so that's the one that I'm going to connect. All right, we have one more side. We're almost done. We're almost done with the lesson, and we're almost done with the whole notes packet. The last page. I bet you thought we'd never make it to page 24. All right, we just have a couple more here. So we're going to do the same thing. So taking a look at the next function, go ahead and write down the transformation in words, and then identify what is the parent function. All right, so negative is on the inside now. So we're reflecting over the y-axis. This one's going down 4. Parent function is square root of x. So on our graph, I'm going to put the original points. And again, with the reflection, you have a couple options. You can go down first and then reflect, or you can reflect first and then go down. I'm going to do mine in an opposite order than I did before. So I'm going to move everything down 4 spaces first. I do my in-between step here in red. Hold on, 1, 2, 3, 4. Okay, so that was down 4. Then I'm going to go ahead and take those, and reflecting over the y-axis, I'm just flipping it over the other way. This point here, this like anchor point stays the same, but this point is going to flip over there. That point that's at 4, -2 is going to flip over to become -4, -2. 9, -1 is going to turn into -9, -1. So the final answer here is just that one there in green. Reflect it over the y-axis and down 4. All right, we have one last type of transformation that we haven't graphed yet in the last problem. I want to show you what it looks like to do the vertical stretch. The vertical stretch is easiest to graph by hand when you're doing the absolute value. So that's why we're looking at 2 times the absolute value x here at the end. So let's just make a quick note here. The way we would write this out is that it is a vertical stretch, and then here's what we're going to say for the 2. We say that it's vertically stretched by a factor of 2. That 2 right there is a fill in the blank. You fill in the blank with whatever number you see in front. If it was a fraction, you would say vertical shrink by a factor of 1/2. If you had a 1/2 in front. Or you can say vertically compressed by a factor of 1/3. So that's how we describe it. Parent function is absolute value of x. All right, so the original points for our original absolute value are like this. Here's what I want you to notice here on this. Actually, we already talked about it earlier when we did the piecewise graph equation for this. The right-hand side has a slope of +1, and then the left-hand side over here is a line that has a slope of -1. The way that this is going to get vertically stretched is that now on the right-hand side, it's going to turn into a slope of 2, so it's going to be steeper. On the other side, it's going to turn into a slope of -2. So the steeper line, that's what makes it look narrower. So let's see if we can do that here. So we're still going to start with our starting point here at the origin. So we're still going to start at 0, 0. Instead of going up 1 over 1, I'm going to go up 2 over 1. Up 2 over 1. Up 2 over 1 until we've gotten a few points. All right, so we've got a slope of +2 on that side. I'm going to connect it. Sure enough, it's a steeper line. On the other side, the slope of -2 is up 2 over 1 to the left. Up 2 over 1 to the left. Awesome. Once we have a few points there, that's what makes that vertically stretched. So the only parent function that I would test you or ask you to do a vertical stretch or vertical shrink is just the absolute value one. So it's kind of similar for the others. There's a few differences, but the absolute value is easy because it shows the slope. If you have like a 1/5 in front, well then your slope is 1/5 on this side, which is not very steep at all, -1/5 on the other side. Like the slope is just what makes it wider. So it's a little interesting thing about that. All right, so we saw how we can take the equation and get the description to ultimately make the graph. All we're going to do here at the end, we have some other homework problems that are kind of like this. We're just going the other way around. So it's giving us the description, and we're writing the equation. Pay attention to the parent functions that it tells you in the equation. Like, it might mix it up. All of these are going to be based on y = x², but really we could do it for any of them. So for example here, if we wanted to go 5 spaces to the left, we're going to add 5 inside of our parentheses. Don't forget to keep it squared on the outside. And then if we also want to go 2 spaces up, we're just going to add 2 on the end. Vertically stretched by a factor of 3 is putting a 3 in front of the x². If it's reflected over the x-axis, we also have a negative in front of the whole thing. Vertically compressed by a factor of 1/2 just means we put a 1/2 in front of the whole thing. If we want to go down 10 spaces, we're subtracting 10. On the last one here, if we want to go 7 spaces to the right, we're going to subtract 7 inside of our function. With this one, it's going to be inside parentheses, kind of similar to what we did before when we went to the left. This is how we go to the right.